Okay.
So our next speaker is coming to us from King's College London, Ruth Gregory.
Thank you, sir. So it's 40 minutes questions, roughly. Yeah. Okay, well, thanks very much, Jeff, for having a birthday, so that I have an excuse. This is my first trip across the Atlantic for 2 years, and it went amazingly smoothly. I even had a friendly immigration official, which is completely the opposite from the first time I flew into O'Hare when I was accused of being a heroin dealer.
What was the evidence?
How are you?
Okay. I shall no comment. So anyway, so it's lovely to be back in Chicago, and the weather is smiling, so that's great. And I must admit to a little bit of imposter syndrome here, because I must be, well, no, Rocky, you're the other one, not a string theorist. But I was here at Chicago when string theorists were starting to get interested in gravity. So that's kind of how I got to working with Jeff. Jeff will be relieved that I didn't think to look for embarrassing photos until after I'd got to London, where I'm still sort of not really quite installed in my flat. So the only thing that I could come up with is this rather nice photo of him with Mike on the slopes in Aspen. So that's kind of a nice one. And I also put up some of the papers that we've done together. And I was thinking, what can I talk about today that kind of represents a little bit about the type of work we did, because I certainly can't talk about moonshine. Drink it maybe, but not talk about it. So as you can see, we did quite a bit with black holes, but I think my favorite title has to be Cinderella Strings. That's one of the best titles ever. This also got me realizing this was back in the day when archive numbers were in like double or even triple digits at most. Really, a lot of nostalgia there. But I'm sure you'll be hearing a little more in Paul's tribute tomorrow about, we were kind of there right at the beginning, the birth, you know, we were like sort of birthing coaches, or maybe I was a midwife or something with the archive. You probably don't remember, Paul, but
I'm going to give credit to Jeff for lots of things, but not that.
Well, you certainly used to have a great script where every time you submitted a new paper, it would always come up as some sort of spoof thing. So that was great. So I decided that I would talk about something that might be of interest to people doing string theory, which is acceleration and black holes. And in particular, a recent paper that's just come out in JHEP with Gabriel Arenas Enriquez and Andy Scoynes. So C metrics and 3D. So there's a lot of C in this. It's about acceleration. So the plan of the talk is a little bit about C metric in 4 dimensions, some C for chemistry, a theorem, though not a C theorem. I thought definitely if I have a theorem, that's my tribute to Jeff. And finally, C in 3. So lots of C's. So first of all, 4D, I'm not really going to sort of get too much into the detail. If you're interested, you can always look at the papers, but I'll try and sort of give some signposts through the work. There's this very peculiar metric as an exact solution in Einstein gravity called the C metric, which looks very much like a black hole in the sense of it has what's almost a spherical symmetry, and it has things that look like a Schwarzschild 1 minus 2m on r, but it's actually dependent on both r and theta, and you see this little a parameter creeping in, which is going to have to do with acceleration. So in a usual sense, so I always think of geometries rather than groups, but the the Newtonian potential multiplying dt squared kind of tells you about the causal structure of the space. So you have horizons if this thing has a 0, and you can see there's going to be one somewhere near 2m. This tells me we're in ADS at the end, and the A tells me that we're in a C metric. So there's also this conformal factor outside the whole thing. And why am I telling you about this? Well, a few years back, I got interested in thinking about thermodynamics of C metrics, so round about some ideas of what's something called superentropicity. But people had thought about thermodynamics, but not actually done it as a full composite system. So this is kind of where this came from. But first of all, I need to sort of give you a bit of intuition about what it means looking for thermodynamics of a composite system. So that K that was floating around tells you you have a conical deficit. So typically when you have metrics, if they're exact solutions, there's a symmetry, which means you have a killing vector. The metric doesn't depend on a coordinate. And so this thing here is like an angle. And if the metric doesn't depend on an angle, you can chop a bit of it out. And that gives you conical deficit. So people thought about this, black holes with strings through them. And that was, I guess, first done by Ariel, Ford, and Vilenkin. But in fact, it's the legitimate GR solution, and you can smoothen it out with a cosmic string. And the deficit angle is related to the energy per unit length of the string. So I guess there's a string somewhere in there. Not really a theory, but it's a string. And K is what measures that deficit. So to do thermodynamics, what we really want to do is we think, let's what happens if we throw something into a black hole, gets a bit bigger. How do we decide what happens? Well, the horizon's always going to be given by F is 0. So you just vary absolutely everything in sight, which means the mass. And if I ignore any charges, I'm also going to just pretend this is just a black hole with a string through it. All I can vary is M and L. So this changes the radius, hence it's going to change the entropy, changes the little mass parameter, so it's going to change the mass. And this changes L, so it's going to change lambda. Please don't ask, how can a cosmological constant change? Just think about inflation and effective vacuum energy.
What about the deficit angle? Wouldn't you also vary the deficit angle?
Yes, but F doesn't contain the deficit angle. However, next slide says that the entropy, because it depends on K, when you want to relate the change in the horizon size to the entropy, you have to vary K to take. That's where it creeps in, comes in through the back door. So your temperature looks like it has the usual definition. Your entropy is still the area, but because you've cut a wedge out, you've changed your area, and hence when you want to relate delta R plus to S, you pick up a delta K. So people had thought a bit about the entropy of these, the thermo of these solutions, but they never really thought about treating the string as part of it. It was more about looking for the entropy with a conical deficit or a temperature. Yes, Andy?
And sometimes people also talk about conjugate to the entropy as a deficit angle at the horizon, right? That's a different thing.
So, do you mean the thermodynamic conjugate? I would have said the temperature was that's the potential associated with entropy.
That's right. So if you take like a black hole solution and you change the periodicity a little bit, the temperature, you'll get a conical deficit angle at the horizon.
The Euclidean, you mean the Euclidean time?
Yeah, so.
This is not the Euclidean, this is.
Right, but, so there would be another way, you could still put a deficit angle, make the thing not smooth at the horizon, I guess, and what if you didn't have these strings? There would still have to be something conjugate to the entropy.
So if I didn't have the strings, I wouldn't have a physical object to actually put through the black hole. So I wouldn't get, this is a real conical singularity in space, you know, and so if I didn't have something to replace that conical singularity, I would say, oh, it's just a GR curiosity, it doesn't have a real source. So I would not really imagine that it would be something that I could vary. But because I can replace that exact conical deficit with a finite width source, I can kind of go ahead and play with it, because I can imagine a process where a string gets captured by a black hole. So you get from 0 conical deficit to a conical deficit. The black hole could then go, and so the conical deficit changes again. And so you can follow that process through and see that if you think about it thermodynamically, the black hole kind of gobbles up a bit of string. But there's no funny business going on in the Euclidean section. So yeah, changing K is related to a change of mu, which allows us to get a first law. So here we've got a sort of fairly characteristic first law where delta M is TdS plus VdP. So this is your extended thermodynamics, which has been quite nicely developed over the last decade or so. But you get this extra piece if you allow this conical angle to change. And so delta mu is multiplied by something that has a dimension of length. Also, the mass or enthalpy depends on this K. This is just the simple example. So this parameter, that's the thermodynamic potential for the tension, we call the thermodynamic length. So in this case, it's just related to the difference between R plus and M. And it kind of has that, it's a bit like what happens with the varying cosmological constant. It sort of reinforces that interpretation of enthalpy. The black hole grows, it swallows some string. So it's kind of part of that same picture. So that was just kind of how does one incorporate a cosmic string or a deficit into a black hole and its thermodynamics. So what happens with the C metric? Well, if you want to add acceleration, you can think of the black hole with a string through it as a black hole with a string coming out the north and a string coming out the south. And if you change the balance, if you say that those two deficits or tensions are not the same, then you've got a net force pulling the black hole in one direction. And so that is the C metric, where the two deficits are not the same. Typically, people make one axis regular and shove everything on the other axis, in which case the deficit looks like MA on K. And so your tension is in a very real sense, the string is pulling the black hole along. And so again, you can use the sort of traditional model for a cosmic string to replace that conical deficit with a proper sort of thick core. So
what does it mean physically to make n axis regular? I mean, shouldn't there be a deficit angle going around the string both above and below the black hole?
no, it's just round on one side. So if you have a
But I mean, far from the black hole, you have a cosmic string going off, and it doesn't
in
create
one
it.
direction,
It doesn't create a deficit.
only sort of around the axis where the string is.
So if I think of this as like a theory with a broken U1, the black hole has to carry some magnetic charge,
Yeah.
and then the flux of that runs down the string in
Yes.
one direction.
Yeah,
Okay.
exactly that. So you could imagine it had only one unit of charge.
Right.
Then you sort of go through your phase transition, the magnetic flux confines, and all it can do is to
Right,
confine
okay.
into one vortex, so it all
Right,
goes
okay,
down to
okay,
one end.
okay.
Yeah.
Okay.
But it's not got that, so normally with just an isolated cosmic string, you have your deficit angle sort of everywhere at infinity, but you're cheating a little bit in a sense, you only see it locally. And so you only locally see it on the one axis in that case. So, okie doke. So the general C metric, if it's in a vacuum, has a sort of partner black hole. It has this kind of structure where you have one accelerating black hole, which is in a causal patch, which is kind of one diamond here, and that has a mirror image on the other side. And so it's as if a black hole's coming in from scry minus and uniformly accelerating out to scry plus. So that's the sort of conventional C metric. But we, when we were developing this, wanted not to have an acceleration horizon, because then you have to worry about what are you taking, you know, the mass. You need a time-like killing vector to think about masses, so we didn't want to worry about the fact that this was a boost symmetry. So we looked at ADS black holes that had one horizon only, which was that of the black hole. And these are called slowly accelerating black holes. So again, pictures, liking pictures. If I set the mass to 0 in that metric, keep AL less than 1, what I have is ADS in Rindler coordinates. What I've done is I've shifted my observer off from the center and I hold them there. And in this case, this is where they're sitting. So it's dependent on A and the ADS length scale. And this is my coordinate system, theta and r. And the dashed line is r equals infinity. So that's a slowly accelerating Rindler. I add the black hole. I introduce the deficit on one side. My black hole is displaced from the center, so this is like a cartoon. And so it's hanging from the boundary. But the string goes all the way to the boundary, so the boundary also has a conical deficit. So that's roughly what it looks like. So then, I don't know if there's any students in the audience, but if your supervisor tells you, oh, this is just a small problem, it'll be done by the summer, take care. That's what I told my student. It was his whole thesis in the end. So it was quite a long story getting these, the full thermodynamics, and in the process we discovered things about normalization of killing vectors and, well, lots of stuff actually, how to compute masses in ADS. So this is the full singing, dancing, rotating, charged, etc., accelerating black hole. You see that F has bits with rotation and charge, and there's a whole slew, you know, the function that's distorting the sphere gets a lot more complex, as indeed does the conformal factor. So that's our full metric. And then the idea was, how do we vary it? And what we found out with black hole thermodynamics was quite often it was done by people just, you know, varying stuff and looking for consistency. And that sort of failed time and again for us. And part of the reason it failed was simply because we weren't sort of stepping back and thinking about what was actually going on. And the key to getting it to work was to realize that our time could potentially have some sort of normalization factor. So that was the sort of key input. Our temperature is done in exactly the same way, Euclidean trick to try and establish, you know, what's the periodicity of Euclidean time. The entropy depends on K again, and also on A. But then we need to find the mass. And so there's various ways you can compute mass. We tried sort of conformal completion. We tried a sort of Sheets ADM type integral. And the one that I'll just quickly sort of show what we did here, you can also do it by looking holographically, just doing a Pfefferman-Graham expansion of shifting from your r theta coordinates to boundary-based coordinates, where your z tells you z goes to 0 is the boundary, and then you choose these f's and g's in order to have the right format of the asymptotic metric, no cross terms, and the 1 over z squared and order 1 piece. So that tells you everything up to a conformal factor, and then you just choose your conformal factor to make life easy. So this is what we got for our boundary metric, which is a distorted sphere. We still have a conical deficit out there, and this was the boundary stress tensor when you calculate it. And so you see it's got an anisotropy, and then you integrate up the energy to get the mass. So this is what the stress tensor looks like. That's where the deficit is. And this is what our mass is. So the mass ends up being really, really simple. But what's alpha? So we know what alpha is for the slowly accelerating Rindler. And in fact, it remains at alpha even as long as you haven't got rotation or charge. So from this, we managed to get a consistent first law with corrections to V, got our thermodynamic length, and of course we got rotation included, which was the really tricky bit. So this, just to show that it was justify why it took so long, really. This is all a set of charges in terms of the metric parameters. So our mass, our T, our S, all these charge, rotation, pressure, thermodynamic pressure. These are our thermodynamic lengths. This is the alpha, the full Monty alpha, and this is this sort of normal psi factor. So that was our sort of long haul, climbing the algebraic mountain. So now to move to a next C, the chemical expressions. One of the things we were then interested in working with these black holes. So one of the things that's quite fun is to try, rather than thinking about what the metric does, because a lot of the times you sort of saw people working on this. Yes, Andy?
Yeah, I'd just like to make a comment. I had a pair of students who did a project all on their own.
Mm-hmm.
I didn't supervise, let alone participate, in which they worked out the first law for this C metric in flat space. One
Yes,
was a year ago and one was 2 years ago.
Mm-hmm.
And they got a very beautiful result, and it would be interesting to see if the lambda goes to 0. Or did you check, do you know about those papers? And you checked?
I do, yeah, because we'd also put some in our final paper. We'd put something in about what the parameters would be if you had an acceleration horizon. So everything is all consistent. Yes. So what they did was absolutely right. Yeah.
What? Yeah.
Yeah. No, it all works. The thing that's interesting though.
It's good to know that because I didn't check it.
The thing though that's you've got to be careful about though with the vacuum is just what your killing vector is, and it's the usual sort of technicalities.
No, it's a very. I appreciate what a hard project it is. Yeah, those C metrics are devilish.
Well, I know you've done some fun stuff as well with the vacuum one. So yeah. So so I think what happened was that when people kind of do some of the sort of black hole chemistry and produce these phase plots, they usually do it using parametric plot, if you're in Mathematica, where you're using the parameters of the geometry. But I think we were really interested to do it directly, to have thermodynamic expressions, because if you want to sort of play, I like to play at times, with things like heat engines, then it's really, really hard to do it parametrically. So Andy and I, that's Andy Scoynes, spent, I think we had this great winter school. I used to go to Perimeter regularly. Hopefully it'll start again. And they sort of essentially shipped us off to this sort of summer camp in winter with no heating in some of the buildings, it seemed, and just left us there for a week. Where you literally couldn't, you were miles away from the nearest place. So we kind of got interested in thinking about the chemistry. And so, what else is there? Well, ice skating, yeah, okay. Winter sports and in Canada. So we just basically, you knock your head until you get the answer. But the one thing that we discovered actually when thinking about this is, and this is where I think sometimes sort of people thinking about the C metric, if you want to thermodynamically at least, maybe don't quite get it right. The real thing is what's your net deficit, your average deficit and your differential deficit. The differential deficit is acceleration, that's the physics of it. The average deficit is kind of your string. And so that's what this C tells you about the acceleration. And so we got, I mean, it's still quite a big slide, but it's slightly less ugly than the previous one. These are our chemical expressions for M, V, T, omega, so that's your angular momentum potential, phi, and these were still the thermodynamic lengths. So with this, it's a lot easier to do things like phase plots and to look at other sort of expressions. So just as an example, you can very easily look at the effect of the conical sort of average deficit. You'd think it didn't make much change, it's just sort of scaling everything, but it sort of decreases the free energy. But interestingly, the Hawking-Page transition happens at exactly the same place. So this is where there's no deficit, this is where you've got an average sort of half of a deficit, and this is where you're tending towards almost cutting the space out. So you kind of see these plots, and they're very easy to make with the chemical expressions. Another thing that was
capital delta?
Delta is like your average deficit. So when delta is it's telling you about the deficit, but paradoxically, and sorry about this, it was just the way we defined it, delta equals 1 is when there's no deficit, and delta equals 0 is when it's maximal. So it's kind of on its head. But in other sort of phase planes, you get these lovely swallowtails. Sort of if you have charge, sort of gradually dropping charge causes a swallowtail to appear in this free energy T plot. But one thing that was noticed by David Kubiznik and collaborators is that that swallowtail would suddenly disappear if you got too much acceleration. And so here, what Andy and I could do was see it completely, prove that it happened and prove exactly where it happened because we had these exact expressions. So the snapped swallowtail here is sort of an example where the plot just suddenly ends. So it kind of snaps at a critical cue. That's sort of fun. So now for the theorem. There's the isoparametric inequality in maths says that you've got a sort of minimal, if you're looking for a minimal boundary area or length enclosing a sort of maximal area. So like if you have a string, what's the biggest area it can enclose, and that's when it's a circle or a disk. So that's the isoparametric inequality. But Svetic and collaborators noticed that this would be a bit of a disaster if it were true for black holes, because it would be sort of saying if you had a given thermodynamic volume, then the round black hole would minimize area, which is really not what you kind of want. You want a round black hole, we know, is kind of the sort of, it's the preferred state of the black hole because your surface gravity is constant all around. So we don't expect sort of wrinkly, wobbly, unpleasant black holes. We like them to be round and nice. So that's why they conjectured a reverse isoparametric inequality and demonstrated it for a range of examples. And so I won't go through it in detail, but again, because we've got these expressions, we can actually combine them to prove a reverse isoparametric inequality for accelerating black holes. And if you have a black hole with a conical deficit, that comes in. So as you increase the conical deficit, you actually give a higher lower bound. So this 1 over delta could become arbitrarily large. So you have this, that's the reverse. I'm just looking at the time, good. finally, home stretch, final lap. C in 3. So this is something where I know people have a few people, there's been some papers in the literature analysing sort of specific examples of solutions of acceleration in 3 dimensions. But there's sort of that some of them, I think, didn't notice some properties of the geometries they had. And also there was a lack of a sort of comprehensive, overview, shall we say. So you can play the same game in 3 dimensions as in 4, and you can find the most general solution. You can rescale, kind of, try and pare it down to the minimum number of parameters, and you find 3 different types of solution, which depend on this Q, whether it's 1 minus x squared or x squared minus 1, or plus 1. And they also have this different, the P is like the F of R before. So these are the full set of solutions of this C-metric form without rotation in 3 dimensions. So if you look at these, the first one, 1 minus x squared you could think of x as a cos theta, but the x squared minus 1, that's not, your x is not so clearly an angular variable, but as we'll see, we can rewrite it as such. So let me just start with sort of going a bit forensically into one of them, which is probably the easiest to visualize, which is the accelerating particle. So you can change those x and y's into something a bit more sort of user-friendly by making a radial coordinate and an angular coordinate, that's that cos again, and see the k's come back in so that phi goes between minus pi and pi, and then we pick the alpha in as before. And so this has, if you look at this, you see that there's no horizon if AL is less than 1, and you have a horizon if AL is bigger than 1. So that's like slow and rapid acceleration. So the slow acceleration is very like the 4D case, except now you don't have a string pulling the black hole or the particle, it's a wall because it's codimension 1. So the presence of this K, which is telling you you're sort of identifying, not quite sort of with the 2 pi, tells you both that you have a conical deficit in your ADS as well as a wall. So if you think about this in 3D gravity, if you have a source, a particle is a conical deficit, and so this has a natural mass, and that looks very like the tension that I was talking about with the cosmic string before. But because you have non-zero extrinsic curvature along these sort of endpoints of phi, you get a domain wall, and that now has a more interesting tension. So it peaks at k equals 2, and then gradually drops. As you increase k, you gradually eat up more and more of the space. So if I get to a picture, so I find it easier with pictures. As I increase A, this was my sort of displaced origin of ADS. As I increase A, I move away from the center. So that's what A does. And then K tells me where I've cut. And so here, K tells me the conical deficit. But what's really interesting is as you cut out more and more, that tension drops. So it's like it peaks when it's sort of almost going across like that. So that's what the slow acceleration looks like. And again, you can do this same holographic computation of the mass, yet a far less friendly expression, arctans and cots, etc., etc. And what's really curious about this is how this either does or doesn't track the intuitive particle mass, which was like the conical deficit. So here, I'm plotting the holographic mass as a function of this conical deficit mass. So you see that there's a linear relation when you have AL is 0, but it stays almost linear. You see here the red is AL is 0.8, and then that's 0.95. And then it's only when AL is getting really, really close to 1 that you see a big departure. So that's kind of curious. So it seems like these are new solutions, but of course, we know in 3D gravity doesn't propagate, so they're not really new solutions. They can't be new. They've got to be just ADS, right? Except written in some sort of gnarly way that you don't recognize it. So the transformation formulae we gave them in the paper, they're pretty lengthy, bit unpleasant, but they do give us an interesting alternative viewpoint because it means we can draw these just as cuts of the cylinder, and it does help to understand our BTZ-like solutions. So remember that our accelerating C-metric in vacuum had this mirror black hole. So this is the picture. I sort of feel like this is a baby album and probably, you know, like it's my baby, so I think this is pretty, but everyone else has got, oh God, come to the end, you know. So don't worry, we're nearly there, okay. This is a rapidly accelerating particle, so you can kind of see the trajectory coming in and going out again. And you see that you've got a sort of acceleration horizon there, that's the green thing, and it's sort of, you know, like a sort of standard type of acceleration horizon. The main difference to the 4D C-metric is we don't have to put in an accelerating partner. It can be pure ADS over here. So you've just cut out this, I don't know if you can really see it, but you've cut out this wedge here in between, sort of inside those dashed red lines. But if you go back to the, see if I can find it quickly, whoop, this picture, you can, that's not obvious, that's a slowly accelerating one, never mind, I thought I had one. You can also, with the rapid acceleration, you can cut out, you can basically go all the way around and cut out the boundary altogether. So the heavier the particle, the more you've cut out, but because these lines here of constant phi sort of arc around in the bulk, they kind of go all the way around and cut off the boundary. So that's a rapidly accelerating heavy particle, which is definitely distinct. You can also accelerate with struts. So here you can see that this will go, this sort of pushing the particle out. And here's a very heavy particle where you've cut out almost all of the space. So that's your accelerating particles. And then of course you can do BTZ black holes, where, just to remind you, the BTZ is a sort of identification of the Rindler wedge. This is the Rindler wedge in planar coordinates. And these blue lines are like the phi lines. But because the metric doesn't depend on phi, they have zero extrinsic curvature, so you can cut and identify. So this is your BTZ black hole. And so it's basically doing this. And I think this is what it looks like in terms of the solution. But if I ask what does it look like from a picture perspective, what's happened is by adding A, you've distorted the way you cut ADS. So we're used to the idea that we have a lot of symmetry, a huge symmetry group in ADS, so we can slice it in all sorts of different ways. But this is kind of the first, I think anyway, the first time that you're seeing this distortion of slicing, which leads to an extrinsic curvature, which is leading to a sort of accelerating BTZ. So this is slow acceleration. Sorry, more baby pictures. This is the rapid acceleration. So here you actually have two horizons. They're really, from a bulk perspective, they're the same one. It's still that the Rindler horizon. But from the black hole's perspective, it's as if you have a second horizon. We also found a new BTZ type solution, which was within the class 1. Normally, you take Y as sort of -1 on AR, but you could take Y positive, and this is where the horizon is if AL is bigger than 1. And so we kind of choose, we put cut our walls so that it sort of sits outside, so we have a range of y that's positive. And so here, what you can do a sort of similar shift of coordinates, but what you notice is that there's a finite parameter range which is disconnected from the absence of acceleration. So this is like a corner of parameter space that only exists when you have A's and K's. So this is what it looks like, both from the formula and from the picture. Oh gosh, formula, baby pictures. Okay.
Can you say what this, so BTZ I often think of as being characterized by having some monodromies in SL2R. What monodromies would
So
you-
I think I would think of that, again, just the pictures of where I cut along the phi's. So that's your sort of winding, going round in the phi angle. So these are I think these are this is, I guess, you cut on the sort of blue line and its partner so that you match across. And I guess your monodromy would be almost the same, surely. It's just that it's distorted and it's got a wall going between the horizon, the black hole horizon and the boundary.
These are finite energy solutions?
Yes. And then just to finish, because everybody's got, the sort of the cursed child or something. This one we didn't spend much time on because it wasn't really like a black hole. It's just like a brain world where you don't get sort of the phi and its mirror image. You have to just take 2 copies of the bulk and glue them together. So I think I'm coming to the end of my allotted time, so I'll just recap. I've talked about how you can vary tension and include that as part of a black hole thermodynamical system. And the conjugate variable is thermodynamic length. It is computable whether they are even though C-metrics are non-static from a certain perspective, and the system is not an isolated black hole, it's a composite system. The key technical point was the normalization of the time-like killing vector, talked about the black chemical expressions. There was a lot that was familiar in 3 dimensions, but quite a bit that was new. And just to finish off, the picture that I put at the start, this is one of those rapidly accelerating heavy particles. So you see the conical deficit, you're cutting out this part. Here's the conical deficit. The red line is the sort of trajectory of the particle. And this is where we've continued across the horizon. And so we can see the full structure in the whole of your sort of global ADS, the cylinder. And so you have no boundary for a while, and then suddenly the boundary pops into existence. And then gradually, for an instant, you get the full boundary. So I think, I'll sort of find this kind of interesting. I'd like to understand bulk picture better, more about the holographic nature of these solutions. And also we had a really interesting comment from our referee who was curious about the fact that if you take the back reaction of quantum fields on your BTZ black hole, just the normal one, then you get, that sort of is equivalent to taking a 4-dimensional C-metric and taking a brane world. And so there's a sort of correspondence, this idea that a black hole on a brane world would give you a quantum back reacted black hole. And so they said, well, what happens for these accelerating 3D metrics, which is quite a thorny question, because someone has actually proven that you can't slice 4D C-metric in any other way than getting the sort of normal BTZ black hole, a la Emperan, Horowitz, and Myers. So yeah, that's a good question. I'll finish there. Thank you.
So what does the area correspond to in the boundary theory?
Sorry, what does this
parameter for the acceleration, A?
Oh, A. So A I mean, for the 3D or the 4D, so you know, the fact that A is there is telling you you have the, in 4D, you have the conical deficit on the boundary. Here, I guess where you have the solutions that are not like this, where you chop out the whole boundary, if you have a wall, the wall goes out to the boundary as well. So it's telling you you've got
Effect on the boundary.
you've got a really distorted boundary.
Yeah, just a comment. If you look at magnetically charged accelerating black holes and you quantize the deficit angles, you can eliminate the deficit angles by uplifting to a higher dimension.
Oh yeah, your
solution.
stuff, yeah.
So if you start with, say, 11 dimensions, and then you reduce down on a 7 sphere, for example, to 4 dimensions, then you can reduce to just this theory, to Einstein-Maxwell theory with the cosmological constant. And if you take a magnetically charged accelerating black hole, magnetic charge then gives you a vibration, the 7 sphere over the sphere with the conical deficits. That total 9-dimensional space can be made completely regular by tuning the.
So it's just a feature of the dimensional
It's just
reduction.
a feature of the dimensional reduction.
Yeah, no, we did look at your papers, although it was kind of
In a good way.
in a good, of course, in a good way, Jerome, of course.
I had a question about the theorem, which I think it just reflects my mathematical ignorance, but you said there's this isoparametric inequality, and it didn't work, or it worked backwards for black holes, but the original inequality must apply only to some class of manifolds. Does it depend on the topology, or what are the axioms that go into that inequality that are violated by a black hole?
Right, Harvey. So, I don't know.
Okay.
Topology. No. It's a good point, actually. It might well be that it's violating some of the because I mean, I'm pretty sure that the isoparametric inequality is going to be where you've got, you know, what your surface inside is completely connected.
Right.
So I guess that would mean it was homotopically trivial or something. So whereas your black hole is quite different, yeah. Yeah, good point. Yeah, yeah.
So if you have a black hole sitting there, there's some picture of maybe where some microstates are that are responsible for the entropy. Now you add a little acceleration. Now you go to some extreme limit where I don't know how extreme you can get as the black hole gets less and less massive relative to tension. Where are the microstates when you get to that limit?
Whoa, gosh, that's a good one. I was just, yeah. You thought about that sort of thing, Neil, didn't you? With strings coming out of black holes and states going along the string.
Yeah, well, so if the horizon curvature gets to be of order of the string tension, then basically the string starts, basically what's happening is that the temperature becomes of order of this Hagedorn temperature of the string, so that the black hole just becomes some giant gas of strings.
In your language.
And it's carried there, still at the hole, and not sort of doesn't propagate along, none of those states propagate along the string.
Yeah, well, there's basically a phase transition that happens when the horizon temperature becomes aware of the string scale.
I must admit, I was not anywhere near that sort of description of entropy, but bad question.
Can your string be blackened?
Blackened.
Yes.
So I guess in these situations, I'm thinking more about where I'm replacing it, you know, with like a cosmic string. So, and I guess, yeah, it could be blackened, couldn't it, if I'm in ADS, perhaps. Haven't thought about that, Neil. Got some good questions here.
Yeah, good question. And we can continue into the coffee break, which should be now. Let's plan to reconvene around 3:40 at the next talk. Let's thank Ruth again.
Yeah, it's interesting.
I'm sure one of those
Actually, I was at the
things
cafe,
that I